I have something I have to do. It's very important before I start. This is for you guys. Are you watching? All right. So thanks for having me back, everybody. I think I was the 9th most popular talk at last PyCon, or maybe 10th. So I'm hoping to up my game this time around. Can you put me on the screen? I'm here today to tell you a sad story, a real-world example of caching gone wrong. I work for St. James Software, and I'm leading their product development team. And so this is a story. It's kind of true. 1974, Donald Knuth, he said this: we should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. And I think we've kind of absorbed this into our culture as software developers, and I'm all on board with this. But there's something that I've learned about that last minute where we leave the optimization to, is that we also leave a few other things to that last minute fairly often. And the next sentence that Donald said was, we should not pass up our opportunities in that critical 3%. And I think because of this last minute crunch sometimes, we do pass up our opportunities in that critical 3%. And this kind of combination of a philosophy that says optimize last and all the things we squeeze into the last minute tends to lead, and I've looked after a few applications over the last few years in different fields, that there's always some part of the application that's performing only just as well as is strictly required. And what I mean by that is that with the current load that the system's under, whatever that load might be, and it might be small load actually, whatever the load is, you've got some things that are sitting somewhere near the limit of their capabilities, and a small change in load or usage of your system is going to push it over the edge. So this brings me to the topic for today, which is caching. This is one of the tools that's in our toolbox for dealing with this 3%, this critical 3% that Knuth was talking about. And what is it? Essentially, a cache is a dictionary. Or to be more specific, it's a way of using a dictionary, I suppose, in order to make your application run a little bit faster. To be specific, it's a trade-off between space and time. So if we have a slow operation that uses a lot of time, we can make it faster by using some more memory. So this is a simple example that should give you the idea. You have a slow operation with a couple of arguments. It's a particular kind of slow operation. It is idempotent. What I mean by that is that if you give it the same arguments a second time, it will produce the same result a second time. And if you have an operation like this, it's a good candidate for a caching optimization. What do? We've got our dictionary. We use our arguments as the key. Look inside that dictionary. Do we already have a result that we've done? If we haven't, we can do our slow operation just this once for that combination of arguments, put it into the cache, and later we'll have it there to use again. Does this make sense? Just want to draw your attention to one fact about this kind of code. It is susceptible to a race condition, a read, update, write type 1. So if you have a multi-threaded application, you need to watch out for that. What am I talking about? You could have 2 threads that are using this cached operation, and both of them could get none out of that cache, and will both execute that slow operation. And this might be fine. It depends what the operation is. But just bear in mind that if you have a multi-threaded application and you're building some caching logic, that you should consider your kind of concurrency requirements there, and you might need a bit of locking in. All right, so on to our sad story. As I said, it's based on a true story. This is kind of in the Hollywood sense, which is to say it's inspired by true events. The details I have kind of messed with for narrative clarity, but you know, it did kind of happen to us. In any case, J5, this is our product that we sell mostly to heavy industrial plants. You don't need to know much about it. It is, except that it is a relatively standardish web application. We use CherryPy as a web server, Genshi for server-side templating, Dojo on the client side for Ajaxy things, and SQL Alchemy as an ORM layer. It is, I think you will have guessed, written in Python. That's why we're here. However, it is generally installed on Windows servers and in our customers' data centers. So that's a slight difference, perhaps, in any case. The caching example that I'm going to use and refer to a few times through this talk is part of our user rights system in J5. So our application's got like a database backend and some forms and things on top of it. And it's actually quite closely related, our forms, to our database tables. And this, our user interface looks kind of gritty. And our customers are used to this idea because most of the systems that we're replacing are kind of homegrown Excel thingy things, Excel and email systems. And so we've got a configuration-based user rights system that lets us essentially specify a SQL-like filter for particular users so we can partition the data. So for example, you should only see information related to the part of the industrial plant that you're working on. The details are not important. What is important is that for reasons that I will not go into and upset me, parsing the user rights definition takes us a while. And also, we have to merge this parsed data structure in a non-trivial way for each user. So suffice it to say that this whole process takes a little bit of time, and we don't want to do it over and over and over again. So what's our solution? Of course, put that completely merged, parsed thing into a dictionary, and we use the guy's username as a key. So that's nice. We only do it once, and then we can keep it in that dictionary forever, of course. Except that sometimes something changes that means that data is not valid anymore. For example, that guy gets moved to another part of the plant, or his role changes, and so the administrator changes the group that he belongs to, and now we have a dictionary with invalid data in it. But that's not too much of a problem. When one of those source bits of data changes, we can remove that entry from that cache. That is called cache invalidation. And this guy, Phil Carlton, he said this, and this is also one of those kind of things you might have heard once or twice, that there are only two hard things in computer science, cache invalidation and naming things. But that didn't seem too hard, so we might have to come back to this one. As I mentioned, we use CherryPy within J5 as our web server. This CherryPy has a fairly standard synchronous request handling model with a thread pool. So you might have encountered something like this before. That's kind of how it looks. So what that means is that within our application, we can process kind of up to n, I think n being 12, mostly, HTTP requests concurrently within the application. And remember I mentioned that thing about optimize last and the last minute. What that has led to in our application is that we have quite a high cost and CPU bound process for generating pages. And when we shipped this to one of our customers that started to push the bounds in terms of the load that the system was on beyond what we had previously encountered, we did find that we had gone over the edge of acceptable performance, and we're finding with a certain degree of concurrent access to the system that we were getting really long delays with giving people requests, and they weren't very happy. And we're Japanese, and unhappy Japanese people, you must do something about that. After a bit of research, what we realized was that we were having some concurrency problems specifically relating to the Python global interpreter lock. I'm not going to go into any details about this because I don't know them. But this is an experiment that you can have a look at it on the web as well. This guy, David Beasley, did it, that kind of illustrates the problem. It's a trivial CPU-bound function, just counts down from some number. If you run it twice in series, so with a single thread, and then run it twice in parallel, so two threads, and this operation should be relatively parallelizable, you'll find that it actually takes longer in parallel. So in other words, it's not only not very concurrent, it also has to do extra work. And those are my numbers that I kind of reran this thing on my own computer. I'm a little bit dubious about the Python 3 one, so I might have done something wrong. But in any case, this is true, I believe. And we read on the internet at the last minute that one way that you can deal with this architecturally is to scale up with multiple processors instead of multiple threads. So you want to take advantage of the multiple processors that your servers have, and this is a good way to do it with Python. So because we subscribe to this software development methodology, which is for those who think Agile is a little bit slow and boring, at the last minute, we rushed in a minor architectural change, and we run multiple instances of our application on that server. Each one of them uses one of the processors or cores using processor affinity settings, and then we round-robin HTTP request to it using Apache as a front-end proxy. And this did make our concurrency problems go away, which is good. So we can actually serve more than like 2 requests at the same time. But of course, brought back our cache invalidation problem. So now we don't have a single dictionary that we need to remove things from. We have n dictionaries where n equals about 8. And only one of those processors actually knows that this needs to be done, because it's the one that got told to change that guy's rights. Are you following me? Does this make sense? So because it was the last minute, we went for a perfectly valid solution, depending on your requirements. So this is a way that you can expire things out of a cache if you have some tolerance for stale data. So what I mean by that is when something's changed, is it actually okay if it takes a while for that change to filter through to all the nodes in your system? If that's okay, then this works fine. So basically we just check every 20 minutes, I think, or something, to see if that guy's user rights have changed. And this doesn't happen very often. And if you wait an extra 20 minutes, that should be fine, right? OK, so that's one scheme you can use. There's some other kind of cache expiry schemes that are commonly used. Why would you want this? If you're just using a plain old dictionary for a cache, you can fall for a problem where you misunderestimated how much space you were actually using. So maybe the objects you're putting in that cache turn out to be quite a lot bigger than you thought, or there turn out to be a lot more of them than you thought. And then you that kind of trade-off that you made, space for time, starts to be a problem because you're using too much space. So there are a couple of bounded caching schemes that you can use. Probably the most common, least recently used, LRU caches. This scheme, it's essentially a fixed size dictionary, and if you need to make some space in it because you want to put something new in it, you remove the thing that was used most longest ago. And there's an example of this in Python 3.2, I think, or something. As a decorator, it's in functools, so you can have a peek at that and have a look at the source code. It is thread safe, so that race condition, they take care of that. And it uses essentially your arguments and coarguments to make a key for that value. So again, this is a way of memoizing idempotent function using a decorator. So you can have a look at that. You could also use a least frequently used scheme. And so this one would keep a counter of accesses and keep stuff in your cache that's accessed often rather than has been accessed recently. Or some hybrid scheme. And it kind of depends on the access pattern of that data as to which of these things is going to be useful to you. And so I think this is part of why this cache invalidation thing is a complicated problem. It's because there's not a silver bullet here. You need to look at the situation that you've got, the data that you've got, how it's accessed, and actually use your mind and think about it. And as it turned out, we were mistaken in our assumption that we had this tolerance for stale data. One of them was the weird mixed up user rights bug, which is that it wasn't strictly a like 20-minute period, so the guy changes and then 20 minutes later you'll have your new rights. We had multiple nodes expiring this data at different times. So as a user, you could log in and one of those nodes would think you had your old rights, one of them that you had your new rights, and because we're an Ajax application, you might actually have parts of the same page rendered with different user rights model applied. I mentioned that we've sold this to some Japanese customers. They have pretty high quality requirements and have a lot of QA staff themselves who test things out. And this led to many long and boring conversations because any time this ever happened, we would have an email and a conversation trying to explain what's going on here. And I don't like long and boring conversations. So, and I've come to realize this over the last little while, that if you don't have a convincing reason for a limitation, you're probably going to have to remove it. And by convincing, I mean that your customer would be convinced by. It's easy to convince yourself, like, oh, yeah, excellent. So we decided we needed a shared cache. Looked around a bit and selected memcached. This is from their website. It is a simple key value store. So essentially, this is a shared dictionary that you can put data into. Forgetting data is a feature, so it has a least recently used scheme in there. And this is an interesting one. Smart's half in the client and half in the server. So they have a kind of distributed model. You can install multiple instances of memcache, and there's no coordination between those servers. So it's up to the client actually to make sure that if you're requesting the same key, it's going to go to the same node, same memcache node. And the other interesting part of this is that the team who produces memcached don't actually produce all of the clients. So you actually have to have a careful look at the client that you selected because half of the smarts are in that client, and it might only have half of the smarts if you're not careful. And in terms of performance, it aims to kind of mimic a dictionary, so order one. Operations that they give you, yeah.
Why do you need a shared cache?
Yes.
Why?
It's a good question. A very good question that we will address. So perhaps I should explain that there are quotes around that. Which is that we thought we needed a shared cache, and it seemed, without thinking too much, a reasonable idea, but no. Anyway, the punchline is coming. So anyway, some operations for memcache. Set, get, delete, the ones you would expect to find. So in our specific case, with our user rights, we make a key up for that user, and when his rights change, we can delete it using the delete operation. There's some other operations that we don't use that might help you in some situation with that read, update, write type race condition, but as I say, we don't use them. You can have a look, so you can bump up a counter or counter down. Internally, it's actually not strictly an LRU cache, so they have kind of slabs based on the size of the item, and it's actually only LRU within the same slab class. So in other words, items of a similar size. Okay, so onto our story. I'm going to give you a catalog of some of the things we did wrong, one of them being that misunderstanding of what we actually needed. I'm sad to say that this is not an exhaustive list, but I've selected the worst ones. Oh, apologies. And this quote is actually not from Thomas Edison, probably, but it might be, and it sounds much better if it is. So first thing that we encountered, leaky abstraction. So we decided to use a Python library, and that obviously makes it look like you've got, when you're writing your code, you've got a dictionary, you've got get and set, awesome. But of course, it's not actually a dictionary because this thing is doing remote procedure calls using TCP to another application. I'm sad to tell you that we actually did manage to do an incredible thing. We have a data structure that we use, a tree, and it can get quite big, like 10 or 20,000 things in it. And we accidentally, at one point, started putting that thing into a single key. So we were pickling it back and forth between ourselves and memcache, which did not improve our performance very much. So bear in mind, if you're doing some remote procedure calls, there are going to be limits that you don't have with a normal method call. So key sizes, there's limits, data size limits, and you should probably know about them. Secondly, the thing about caches is that they are made to be transparent, so they don't actually change the external behavior of your system in any way. So from like a testing perspective, you might not notice if you're not actually using your cache, even though you thought you were using your cache. And we've introduced along the way a couple of changes here and there, maybe we produce the key name wrong so that we don't ever use the same key name again, or just plain old silly bugs where we just don't even use the cache at all, through to more sophisticated reasons, like maybe if you're using an LRU cache, it's just a tiny bit too short, and you keep kicking things out of the cache that you're going to need to use immediately. In any case, I would suggest if you're using a caching scheme that you test with reasonably appropriate data sets, because that would be the best way to find out whether you're actually using them or not, and maybe publish and look at hit and miss statistics. Have a star there because note to self, we should probably do something like this. And then, oh, I forgot, of course, unit tests, which I forget sometimes. Maybe you should have some of those. All right. Another thing that we did, I am a fan of minimizing the kind of configuration effort that you have. So when we add a new feature, I like it to be added with reasonable defaults. But of course, unreasonable defaults can be a problem. This is in our startup code, or was. What it's saying is, if I can't find memcache right now at this moment, then I'm going to fall back and use a dictionary. And I think there was a kind of conceptual model that we kind of had, that memcache we had added. It was kind of an optional extra component. It was nice if it was there. If it wasn't there, it's cool, use a dictionary. But of course, sometimes things don't happen exactly as you had hoped. Here's an email from one of our customers. And perhaps there might be an error starting service memcached. Who knows? And then, of course, having something in the wild for a while, you start to bump into some of the other things. And we found in our client library a few surprises. Some inconsistent handling of stale connections. So we had one system that wasn't used 24/7 as most of ours are, but was left unused for sort of 12 hours at a time. And in the morning, when people started to use it again, they would start to see the connection dead error. And it genuinely was dead. You had to restart all of our services to make it come alive again. An interesting approach to thread safety, you can look for yourself, Python memcached. And some errors swallowed without raising exceptions, which annoys me a little bit. And one unit test. So there have been one or two bugs introduced along the way. Most recently, new line characters are important in the protocol to memcached. And they used to notify you if you had a new line in your key name, but no longer. Now it just breaks the protocol. So, of course, all of this investigation led us to grant you the obvious statement that we had added not a new optional extra component, but a new critical component to our application. And when you do this, I would urge you to make sure you've covered your bases. Are you monitoring that thing properly? Do you know where it's logging to? And do you ever look there? Are you measuring anything about it? You need to answer these questions. What do we do when it's not there? At startups, in our case, we introduced a new version of that weird mixed user rights bug. And what do you do if it's not available during a particular operation? So obviously for a cache, a read or a write is probably OK if you can't get through to the memcache, because you can get the source data yourself. But the way we had built the system, we actually needed that delete to work because we were abusing memcache and using it as a way to invalidate our caches across our system. So when the guy's user rights changed, if we didn't get through to them on the delete, what were we supposed to do? Do we just try again once, 2 times, 3 times, 10 times? Do we need to persist this through the database and start creating our own guaranteed delivery mechanism? Surely not. So when you need a transaction, you should probably use a transaction rather than trying to build a transactional model yourself. I suppose that's an easy thing to say. In any case, this led us on to the next iteration in our process and this is something that can work for us because we do have a relatively low load. So we've added a table to our database, realizing that when we change this data in our database, we need a guarantee that at the same time our caches are going to be invalidated, because we've kind of made that assumption in our application. So we're using the database. We have a table that stores a version number for a cache that we've given a name. and that's basically a group of keys. We build the key name through the memcache, including that version number in it. So the picture up there is suggesting that because it's red, that arrow was a cache miss, and then after that we will have a cache hit. I hope that makes sense. So when somebody's writes change, or for our various caches, when we change some of the source data that we care about, we can bump the version number within the same SQL transaction. Now, this, of course, raises an interesting question. How do you make sure that you actually see the new version number? Now you're just having to do another query from another table instead of the original query from the original table, and that's a fair point. But in our particular application, what we're doing is we do that check of the cache versions at the start of our request processing, and we're not processing so many requests that that's a performance problem for us. And so we can keep that cache just for the duration of the processing of that request. The next time we get a request, we'll get a new cache version. So we've got a different key name now for that key and memcache. So we'll miss and then be able to put it in. The old keys, they will still be there, but will eventually get flushed out by the least recently used algorithm. So we don't need to do any kind of deleting of things, which is probably good. But of course, this brings me back to your original question, which was, you got a lot more, good. Why did we even do this in the first place? Were we solving the right problem by saying, we need a shared cache without thinking about it too much? And no, of course we weren't. Because we don't actually need that shared cache. We can use the dictionaries that we've got and still flush them out this way. And there would have been some alternatives that would have made more sense. What we needed was a reliable inter-process communication thing so we can make sure we can keep ourselves in sync. In any case, so that's what we've got there. And what's interesting about this is that it does actually bring us more in line with what they made memcache for in the first place. So this is from the memcache website. Memcached allows you to take memory from parts of your system where you have more than you need and make it accessible to areas where you have less than you need. So that's an interesting statement. It is explained a bit better with a picture that they've got. So without memcache, if you've got these in-process caches, which is what that top thing is, that's essentially our dictionaries. You've got to have the same keys showing up in each of those caches. So if that makes sense. So you're using in total more memory, or you have less memory in total available to each of your web servers than you do with memcache, because that one key is stored only once. So what memcache is giving you here is a way to have a more efficient use of memory on in your system from a caching perspective. So did we do the right thing? Would we go to the trouble that we had to go to get memcache into our system if we had used our brains a bit harder before? I think not. Because if you are adding like a new application to your stack, there's a whole lot of work that has to go into that. It's not just like, oh, let's just have memcache, cool, like apt-get install memcache. You need infrastructure for monitoring and management. You need to understand this thing, and if you've got other people, system administrators looking after it, they need to understand it. You need to be able to debug and support that thing. And for us particularly, you probably will have some pain on Windows. This is how you install memcached on a Windows machine. You do some research, and you find that there is a Win32 binary version of memcached available here. You feel a little bit nervous, and you look further, and you find one here. But it comes with no promises and no support. Anyway, there's a longer tail there, and you can talk to me about it. We did find a way of reasonably doing this, but this was misunderestimated up front. So anyway, if I can bring us back to what Knut said, that we shouldn't pass up our opportunities in that critical 3%. The question is, if you leave optimization till last, are you going to pass up on some of these opportunities? And I think what Knut was thinking about, in my mind anyway, was a kind of optimization at a micro level. I'm writing this method, and I want it to be super efficient, so I'm going to use this kind of weird way of writing it, and I'm going to read on the internet about how I can optimize this little thing. And I totally agree that doing that optimization up front is probably going to be a waste of your time. And I think Simon actually spoke about this yesterday, the fact that for performance, you might not need just like an optimization of the thing we're currently doing. You might need some new ideas or a different way of thinking about it. And it's worth having those new ideas up front rather than after you've kind of committed yourself to a whole lot of work and pain and suffering. So be thoughtful and be scientific. So I think you can quite easily set up a little experiment that can help you with some of these decisions up front. Like, are we actually solving the right thing? Are we doing the right thing? That could be a thought experiment, the like mathematical thing written out on a napkin, or you can just do like some quick code to validate some of the questions you have. So, for example, as I started thinking more about this thing, why do we have memcache here? The database itself has a cache, and we just got one of those. So, how much faster is it actually if I'm kind of essentially using memcache to keep the results of database queries that, if I'm doing them often, are probably in the cache of the database anyway? So you can quickly do a little experiment to see what is the order of magnitude difference in that. Yes. So I think I've got about a minute left. So for that last minute, I will try my best to answer your questions.
Okay, so it looks to me, so please correct me if I'm wrong.
Yeah.
You didn't want to solve this in Python, so you went to processes.
The GIL thing?
Yeah.
Yes.
Okay, but you have a classic concurrency problem here called the readers and writers concurrency problem. And you are not really creating any concurrency mechanisms to solve that problem.
Okay, yeah.
That you do. So you have deeply unsafe code there. Why are you not doing it in Python? Firstly, you should.
Yes.
I don't know. I haven't done multi-threading in Python, so I don't
Okay,
know.
yeah.
Readers, writers, locks, they
Yes,
should have.
yes, yeah.
That's what you should use it.
Yeah.
What you're doing is never going to work.
So,
Never.
so I think, so
No,
if I can,
so
yeah?
Scientifically speaking,
Yes.
you need to look at multi-threading theory,
Yes.
concurrency theory. This is a problem people have solved it, and you need built-in mechanisms in your language to solve it.
Yes.
Hacking it yourself is going to create code the Japanese will never be happy ever.
Fair enough. Yeah. So I think if I can answer the first question, which was about the GIL and the concurrency issue and why we even went to multiple processes in the first place. Yes. So I think I wasn't involved actually in that at that time, but so I'm like, but having said that, the concurrency problem actually wasn't about concurrent access to resources in the strictest in that sense. Okay. So it wasn't anything to do with caching, actually. So our concurrency problem there was to do with the fact that our application was a heavily CPU-intensive process, and it was running into concurrency problems directly because of the way that the Python language handles that kind of concurrency, or that kind of process, if that makes sense. So we weren't spending lots of time waiting for data or like, as you say, fighting about reading and writing. We were actually spending a lot of time thinking in like processor sense. And that was what was bottlenecking us. So it was access to the CPU that was causing the bottleneck for us, not access to resources.
Thread management. I mean, that little program
Yes.
you use to test, your thread efficiency in Python.
Yes. Yeah.
It's not going to keep your CPU very busy. It's going to spend most of its time juggling threads.
Yes, exactly. So that's precisely what happens. And our application was kind of similar to that one in the sense that it ended up spending most of its time juggling threads instead of actually producing what we wanted it to produce. And the contention wasn't in resources. It was literally like just the way the process worked. I don't know if that answers the question at all on that one. So, yeah.
Be safe.
Oh, absolutely, yeah.
Safe, then
Yeah.
it's game over.
Yeah.
I mean, one of our processes just writes, the other one's called slave reads.
Yeah.
It's a reader's writer's problem. So we have one writer and who needs to lock everything down when it's writing. And you've got multiple readers who can read concurrently if no writer is writing. It's a classic concurrency problem that has been solved a long time ago.
Let's just do something about this.
Yes.
You need a
Yes.
reader-writer lock.
So the database does take care of that.
I don't know if Python has it. Does anyone know?
So it actually wasn't to do with access to that data, the reading or the writing at all. So it is now, yes. So we made it into that. Yeah, absolutely, yeah.
You mentioned at one point you guys had very large objects being used as keys.
Not as keys, sorry,
Well,
as values.
But values that you store.
Yes.
Have you since just reduced that, or have you split it up into multiple caches with multiple storage and aging?
Yes,
types?
that was just a plain old-fashioned mistake. It wasn't an intentional thing that we had done. It was like, oh, it's a dictionary, put an object in it. So yes, we split those things up into the appropriately sized things. Yes.
So it's just an observation.
Yeah.
Memcached, really, the problem with memcached is you've got multiple nodes synchronizing the data.
Sorry, say that one more time, a bit louder.
When you've got memcached and you've got running on multiple nodes,
Yes.
you sometimes have issues synchronizing the data between them.
Yes.
You've got to almost build your own solution on how to use memcached.
Right. Yeah.
Simple way to bypass all of that is use Couchbase.
Right.
It's forked memcached,
Yes.
and it comes with pretty much everything that you need.
Okay, so we've got a suggestion, especially if you're looking at the distributed model for Memcache, which we aren't, that you might want to look at Couchbase, which adds some additional stuff on top of that to like manage the synchronization of those caches and some of these cache invalidation problems.
Is Memcache guaranteed thread safe for multiple processes writing to?
They do have some like reasonable atomicity guarantees, yeah.
Reasonable guarantees.
I believe so, yes.
I think it's atomic. It's either guaranteed.
Yes,
or not.
it's atomic.
Yes.
The reason I'm hedgy is I just haven't looked very carefully, but so the internet tells me.
Question, 2 parts.
Yeah.
How long ago was this that you switched to Memcached?
Uh,
And the other part is,
yes.
since switching to Memcached,
Yeah.
have there been caching solutions where you haven't chosen to use Memcached?
Right. We switched to Memcache a couple of years back.
Slowly and tortuously.
Slowly and tortuously, yes. So I guess, yeah, it's been a few years, let's say. Yeah, exactly. And yes, there have been some things. So actually, you know, I said I took some poetic license. That like data structure for the user writes, you can't really put that thing into Memcache because then you'll have that pickling back and forth thing. So that is actually cached in memory, in process. But there's a lot of other stuff that is cached in Memcache, and some parts of that are cached in Memcache. Yeah.
Hi.
Simon, hi.
At time.
Okay,
I
cool.
don't want to eat panel's time
Yes.
too much. So I'd like to thank Matt and
Cool.
hopefully this lively discussion and continue with tea.
Yes, yeah. So please tell me if we've made another terrible mistake. Apparently you think we have.
So if you get all of the panelists